applications. So other than that, a reminder that I am here Monday and Monday and Wednesdays from 1 to 2, and on Saturdays from noon to 2 for Zoom office hours. Feel free to stop by with any questions, and of course, send me anything if you want through email, through Canvas with any questions. Okay. So anyway, with that in mind, and let us continue. Now we're going to have chapter 14. It's pretty short, fairly short. It takes a little bit longer than the other ones. And then we have, after this, we have chapter 15, which that one is short. So the plan is we finish 14 today, more than likely finish 15 on Tuesday, and then open that the rest of the time if you want for questions. And then next Thursday will be another question session. So, now's a good time during that time period to come in and with any questions you may have concerning any of the worksheets or whatever the problems. There is a previous exam from previous years, final exam. That's a good resource on the course website. You might want to take a look at that. There is some homework on the course website for other sections that have done that. The keys uploaded, that's another good resource. Okay. And don't forget, I do record these sessions and I do upload them to the YouTube if you want to view them again. All right. So let us begin with chapter 14. Now, 14. We're bringing in material that we worked with before. Before we dealt with polarity. So you may want to go back and refresh your memory about polar compounds, all right? Because this is where they come into play. These are what are called intermolecular forces. These are forces that occur between molecules as compared to that's INTRA, forces within the molecule, and those deal simply with the type of bond that they have, be it polar bond, be it non-polar bond, or an ionic bond. Okay, and we'll be touching on both topics during this chapter here. Okay, now, like I said, intermolecular forces deal with forces with other molecules. In this example here in this diagram, you see we have looks like two diatomic molecules, and they are interacting with each other here, denoted by that dotted line. Those aren't bonds, and those are just forces of attraction with each other, okay? They're much weaker than chemical bonds, but nevertheless, they're there. Some of them are pretty strong, and some of them are fairly weak. We will talk about 4 of these type of forces. These forces are what determines the properties of a lot of chemicals, why some chemicals boil at a very high temperature and others boil at a very low temperature. And they're all related to the intermolecular forces, and they're all related to a compound being polar, non-polar. All right, so let's take, well, for example, before we proceed, bonds versus IMF interactions, okay? In this example, we have hydrochloric acid, one molecule. We have a bond between the hydrogen and the chloride. Now, refresh your memory about that. Remember, we talked about polar bonds and nonpolar bonds. When we have nonpolar bonds, the 2 atoms that are together are sharing those electrons that are in those electrons in that bond. There's equal sharing, okay? When there's unequal sharing, like hydrochloric acid, we have a polar bond. Recall that was related to EN, electronegativity, okay? And the atom that had the highest electronegativity was fluorine, okay? And the trend on the periodic table was across the periodic table, En increased, and up the periodic table, En increased, all pointing toward fluorine. Now, here we have two atoms that are dissimilar, okay? The fact that we have hydrogen and chloride together automatically tells you we got a polar bond, okay? When they are the same, like a diatomic oxygen or bromine or chlorine, then we have a nonpolar bond. Now, the other aspect was that, if you recall, we drew an arrow, and we drew an arrow from hydrogen to chloride with a little plus at the end of the arrow. That was a dipolar arrow. And the reason it went toward chloride, because between hydrogen and chloride was stronger in electronegativity, okay? The result was that it left, remember this, partial negative on the chloride side and a partial positive on the hydrogen side, okay? Not a full charge, but a partial, okay? So now you can see that the negative side can interact with another molecule of hydrogen chloride on its positive side. That's the type of forces that we are working with and dealing with here in this particular chapter. So you got to refresh your memory about polar bonds and which direction that polar bond is going. Okay, let me erase some of this, getting too crazy there. Okay, so you can see in that example at the bottom, that blue dotted line is the partial negative of the hydrochloric molecule on the left interacting with the partial positive of the hydrochloric acid on the right. And depending on the strength of that interaction, can define things like boiling point, things like vapor pressure, things like surface tension, and even things like viscosity, how thick something is. We're going to talk about those here in this chapter, okay? Now we're going to do a lot of compare and contrast between molecules. You know, we can't actually tell you absolute values, but we can compare based on the polarity of the molecule, which one's going to have a higher boiling point, which will be more viscous, which is going to have a higher vapor pressure, and which will have a higher or a greater surface tension, all based on polarity. So there's 4 types of intermolecular forces. Okay? Again, I repeat, these forces are forces of molecules with each other, not forces involved of molecules within themselves. Okay? So the first type is what we call, get my cell phone to work here. The first one is called the London Dispersion Forces. Now, these are, I think, very straightforward to determine because all non-polar molecules, the only IMF forces they have is this one here, 1. And if you recall, the diatomic molecules, have no fear of ice cold beverage, are all nonpolar. So the only force they deal with is London dispersion forces. There was another one that I said earlier to refresh your memory was the bond between carbon and hydrogen. Okay, though we have 2 different atoms here, the electronegativity of these two is pretty much the same. The result is that that bond is nonpolar. And so all of the diatomic molecules, I denote by X here, bromine, chlorine, hydrogen, so on and so forth, okay, are nonpolar, and the carbon-hydrogen bond are nonpolar. Therefore, the only force they deal with is the London dispersion forces. Okay. Number 2 force That's called the dipole forces. Okay. In order for them to work or to be there, they have to have a dipole in the bond. Previous slide had two molecules of hydrochloric acid. Two molecules of hydrochloric acid. Okay, like that. And it showed a dotted line between them, simply because we had a partial negative on the chloride and a partial positive on the hydrogen. Okay, so we have a dipole here and a dipole here, hence dipole forces. Okay, the third one, excuse me, is called London bridging forces. You'll also hear or see the term bonding in lieu of bridging. Right now, they're trying to convert the name to bridging because the hydrogen bonding infers there's an actual bond there, but it's not. But we're gonna use it interchangeably. Hydrogen bridging forces. Okay. Now those forces are polar molecules, but there's only three types, and we'll give you an example of those here in a bit. And those are interactions between hydrogen bonded to either a nitrogen, an oxygen, or fluoride. Okay, so we'll talk about that in a second. And then finally, the fourth bond that's involved here is called the ion dipole forces. Well, the key word is ion. Okay, so that means we're dealing with an ionic compound, a metal nonmetal. And the majority of the time, these interactions, you'll find them in aqueous systems. So we're looking at water systems in which there's been a salt dissolved in there, like sodium chloride and salt, magnesium chloride. These are ionic compounds dissolved in water. Okay, so when you see ion, think ionic compound, and dipole forces, you're talking about water, and water has a dipole. Okay. All right. Well, let's talk about these dispersion forces for London force. Okay. These forces are pretty much temporary. And they don't occur. They're not permanent. Like hydrochloric acid, that's a permanent dipole. Well, with these are nonpolar species, and we can induce or create temporarily a dipole, but not very long. It has to do with the electrons around the molecule. And you probably have done something like this at home. I'm sure you have taken a balloon, and I use this example because it really demonstrates the London forces. If you take a balloon and you rub it on your head, you fill that balloon up with electrons. You transfer those electrons from your head onto the balloon. Then you take that balloon and you transfer it to your chest. Doesn't it stick? Yeah, it sticks. It doesn't stick very long, but it sticks there. You have created a temporary dipole. What has happened is there's electrons on the surface of your chest or any area on your body. Everywhere around us, there's electrons. Now, what you have done is by bringing that balloon close to the surface of your chest, those electrons on the surface of your chest are negative charge, just like the electrons in the balloon. They're negative, they repel each other, okay? Meaning that those electrons that occur on the surface of your chest are pushed back into your chest, leaving a positive charge temporarily on the surface of your chest, which then causes the electrons of the balloon to attract to that positive area. Hence, the balloon sticks. Okay? Because you know that balloon won't stick forever, plus that interaction is pretty weak. That balloon comes off very, very readily. Okay? And so you'll see this happen with nonpolar molecules. We'll give you a little example here in a second. All right. Now, one word about London forces when they're nonpolar. bigger molecules have stronger or more London forces. It makes sense if you think about it. I got more electrons. If I compare fluorine gas, F2, with, say, bromine, a bigger molecule, bromine, Br2, would have more electrons and hence have more London forces involved. Simply because it's got more electrons, that's all. And how that works is just like the balloon thing. We have these electrons that are coming closer together in this area here, and they push the electrons from one molecule away, resulting in a temporary partial positive and a partial negative interaction, just like two magnets, north and the pole, are going to attract each other, okay? And we form this interaction in the middle. However, those interactions are weak, not as strong as some of the other forces we're going to talk about. But this here, these are nonpolar molecules that have been temporarily induced a polar compound, but temporarily. Okay. Now, with respect to dipole forces, I showed you the example of hydrochloric acid. Now, in this case, we have a permanent dipole because of the nature of the compound. In this example here, we have hydrochloric acid, which we have right here. Big old chloride sitting there because it's more electronegative. We have a dipole bond, a polar bond here because there's unequal sharing. And so we have created a permanent negative, partial negative there, and a permanent partial positive on the hydrogen. Okay? It's a permanent dipole. That results in this interaction here, denoted by that line, with another molecule. Now, there's not a bond there, it's an interaction. Okay? And that interaction, depending on how strong it is, does affect the properties of the molecule, like the four properties we're going to talk about: boiling point, vapor pressure, viscosity, and surface tension. All right. So, in order to have dipole forces, first of all, these forces are much stronger than the London forces. Okay? And in order to have a dipole-dipole interaction, they must be polar molecules. Okay? Polar molecules. Right. Now, the third type of the three, very strong, the strongest there is, these three forces. We call that hydrogen bridging forces, also been noted as hydrogen bonding. Okay? Now, there is a dipole involved. If we look at the molecule here of water, we got a dipole there and a dipole there because oxygen is a lot more electronegative than hydrogen. So we have two dipoles. Okay? And then there's that interaction with another molecule of water, again shown here because it's the partial negative of the oxygen is interacting with the partial positive of another molecule of water. Hydrogen bridging only occurs for those hydrogen bonded to fluoride, oxygen, and nitrogen. Okay. Yes, they have a dipole, and there's dipole interactions. However, because they are bonded to fluoride, oxygen, and nitrogen, otherwise as NOF, then that force is stronger than the dipole-dipole interaction. Okay, so the majority of the force involved for those guys, those three, are the hydrogen bridging forces, which is the strongest one. So you can see how complex these interactions can occur by the picture on the right. We have a lot of hydrogen bridging going on. And it's one reason water, for example, takes 100 degrees Celsius temperature-wise to get it to boil, because it needs to break up those strong interactions. Other things like ethanol, alcohol, it also has hydrogen bridging, but they're weaker because of the nature of the compound. And it boils at 78 degrees. So that hydrogen bridging does have a lot of effect on the physical properties and a lot of molecules. Okay, this one here kind of demonstrates again the interaction of the hydrogen bridging, which is much stronger than the dipole-dipole. Okay, but much weaker than bonds, the actual ionic or covalent bonds. Keep that in mind. These are relatively weak interactions. Okay, weak interactions when compared to bonds. Now, with respect to the fourth example, we have ion dipole force. Now, the key word being ion, meaning that we have an ion of some sort in solution. This is represented here in that diagram where you have sodium, okay? And then it's interacting with all the partial positive, negative, areas of water, which are denoted by the red sphere. The chloride of this, is sodium chloride, could be over here on the right side interacting with the positive, because the chloride has a negative that's interacting, okay? So in order to have an ion dipole, we're talking about an aqueous system, water, and some type of ionic compound, okay? And refresh your memory, is what's an ionic compound? That is a metal and a non-metal combination. All right, now when we compare the difference between the bonds and the forces, when we speak of bonds, we're talking about, if it's ionic bonds, refresh your memory, that didn't come out very well, let me erase that again. Ionic bonds, that is between a metal and a non-metal ions together. Then we have polar covalent bonds, that is a combination of two nonmetals, and they're polar because two different nonmetals. They're polar because one of the atoms has a higher electronegativity, creating a dipole in that bond. And then we have the non-polar covalent bonds, such like the diatomic molecules and carbon-hydrogen, okay, non-polar. Now, with respect to forces, London forces, any non-polar molecule, once you have determined that it's a non-polar molecule, the only force involved is the London force, okay? Well, if you determine it to be a polar compound and it doesn't involve nitrogen, oxygen, or fluoride, then you're dealing with dipole-dipole IMF. If that polar molecule involves a hydrogen bonded to nitrogen, oxygen, or fluoride, then you're dealing with hydrogen bridging forces or hydrogen bonding force, okay? And then finally, you have a polar a polar molecule like water, an aqueous system. You have an ion dissolved, and the only force involved there is simply the ion dipole interaction. Okay. Now, we had a table here, and the first column is asking you to determine first, is it polar or non-polar? And then based on that information, determine what is the strongest IMF interaction, okay? This is where, recall that we did our Lewis structures. Our Lewis structures, we were able to determine based on the structure we come up with and the valence electrons, a structure, and then determine whether something was polar or non-polar. If you go back and check your notes, carbon dioxide is nonpolar, as you saw that. Now you might ask, well, wait a minute. I got carbon and oxygen, okay? That would suggest a polar bond, which you'll be correct. But the Lewis dot structure, after we're done writing it, refresh your memory, we had two double bonds, okay? And yes, there's a dipole going from the carbon to the oxygen in both directions, okay? But based on their position, these two dipoles cancel each other out. So you have a polar molecule, polar bond in the molecule, and if those cancel out with another polar bond, then you have a non-polar species. Okay, and that is why carbon dioxide is non-polar. Okay, even though that it has polar bonds. That the fact that it's non-polar, the only force involved there is London forces. Okay, now take a look at the phosphorus trifluoride. When we draw the Lewis dot structure, it'd be just like ammonia, very okay. We will end up with the 3 fluorides bonded to it, and we end up with a lone pair in the central atom. And recall when we were doing that chapter, I said if you end up with a lone pair on the central atom, the polarity is a polar compound. 1 lone pair, 2 lone pairs, even more polar. So if you do the Lewis dot structure and you got lone pair in the central atom, there's no question you're dealing with a polar species. Therefore, you are dealing with dipole-dipole. Why dipole-dipole? Because notice phosphorus trifluoride, there's no hydrogen involved. Plus, it's not part of the central atom, is not nitrogen, oxygen, or fluoride. Okay, therefore, the only force they have is dipole-dipole. Okay, second one here, hydrofluoric acid. Okay, polar compound. Okay, just like HCl. Okay, you might think, okay, dipole-dipole, hydrogen bridging, right? Well, look at it. You got hydrogen bonded to fluoride. That should tell you right away, hydrogen bridging. So we got a polar species, hydrogen bridging, because we have hydrogen bonded to fluoride, which is one of the 3 atoms. Earlier I said that all the diatomic molecules are nonpolar, but I also added any carbon-hydrogen bond. This here is what we call we call that a hydrocarbon, because all you see is carbon and hydrogen bonded, nothing else. Okay, that tells you right away that you're dealing with a non-polar species. Therefore, the only force involved is London forces. Okay. Finally, down here, 2 things that should catch your attention. We're dealing with potassium iodide, a ionic compound, because you got a metal, non-metal, plus you're told AQ, aqueous. So the only thing here that could be involved is the ion dipole forces. Okay. All right. Briefly speaking, they're talking about the Coulombs Law here, and all we're going to just say here is 2 things. This is a law that explains or determines the interaction or the force between 2 charges. Okay, be it these magnets or be it an electron and a proton. Okay, but the thing to take away from this, it just says this: that Coulombs Law states that the attraction between 2 charges is proportional to the charge of magnitude. Okay, proportional, meaning that when one variable goes up, the other one goes up accordingly. That's proportional. Okay. So what that first part says, if I increase the magnitude, the intensity of the charge, my force is going to increase correspondingly. Okay. The second part says that it is inversely proportional to the square of its distance. Okay, well, let's attack inversely proportional. That simply put means that when one variable goes up, the other variable drops. That's all that it's telling you. But it drops such that the distance between them drops by the square of that distance. And so if the distance starts off at, say, 1 centimeter, and then you double it to 2 centimeters, now that force is 2 times square, so it's just 4. it is reduced by a factor of 4 of some amount. Okay, maybe it'll be a little bit clearer when I bring the equation here. Okay, Q represents the charges. And if you think about it, K is nothing more than a constant. We can ignore it for right now. Just a constant. It stays the same. R represents the distance between them, squared. And so if we keep R constant and we change either Q1 or Q2, we double it, we triple it, that total force goes up correspondingly. Okay? Now, however, if we change the distance between them, it will change by the square. So let's say Q is constant, both Q's are constant, obviously K is constant, and R starts off at 1 centimeter. Well, 1 square is 1, so our force is equal to whatever that number is. But this time, let's take that distance and double it, okay? So we go from 1 to 2 centimeters. Well, 2 square is 4. And by increasing, doubling the distance between those two charges, drop the force by 1/4, okay? So the force drastically increased. You can also see this too if you ever play with magnets. Obviously, if I put two north together and I bring them together closer, and the closer I bring, I can feel that force just really pull against each other. And as I separate them, that force diminishes greatly. Okay, that's basically all they're telling you there. All right. All right. So with that being said, let's take a look at this table. They're asking you to choose the bond or the IMF described in each of the questions. Now, these type of questions, you got to be careful when you read them. Are they asking you about the bond, or are they asking you about the interaction with other molecules? Okay. So the first one, what holds the atoms together in one ammonia molecule? Okay. The key word here being one. And let me change the color here. The key word being one. Okay. So here we're talking about the bond itself. Let me erase that. One molecule. So we're dealing with the bond. So in that case, if we look at the bond between nitrogen and hydrogen, it's a covalent bond, but more importantly, it is a polar covalent bond. Okay. Second question says, what is holding the sodium ions in water? Again, key parts, we're dealing with water and we're dealing with ions. Well, of the four forces, the only one that has to be here is the ion dipole. Okay, because we're dealing with ions and we're dealing with water. Water being a very polar solvent. Third question, what is holding 3 hydrochloric acid molecules together? Again, the key word here being 3. So we're talking about the interaction of other molecules with each other. Okay, so therefore we're dealing with IMF. Okay, well, which one? Well, it's not London forces because hydrochloric acid is polar. Okay, so then that leaves us with either, and it's not ion dipole because we're not dealing with any ions. So that leaves you with dipole, or hydrogen bridging. It can't be hydrogen bridging because we're not dealing with nitrogen, oxygen, or fluoride. Therefore, the only one left is dipole. And that is the forces. Next one says, what is holding the ions together in salt? So in chloride. No mention of water here. They're just talking about what is holding the ions together, okay, in salt. So we're talking about anionic bond. That's it. Then what is holding 4 H2O molecules together? Now we're dealing with more than one molecule, so that tells us that we're dealing with IMF interactions, okay? Obviously, water is polar, so London forces are not there. We're not dealing with ions, so that force is not there. So we're left with dipole, or hydrogen bridging. The fact that we got hydrogen bonded to oxygen tells us we're dealing with hydrogen bridging, okay? Water always has hydrogen bridging or hydrogen bonding. And then what holds nitrogen gas molecules to each other, okay? To each other, meaning we're dealing with with interactions with other molecules, okay? So we determine nitrogen gas. It is part of the diatomic molecules, which means it is nonpolar, which then tells you London forces, the fact that it is nonpolar. What is holding the oxygens together in an oxygen gas molecule? Here we're dealing with the bond, talking about what is holding them together, okay? It's a covalent bond. The two oxygens are the same, so it's a nonpolar covalent bond. Then finally, the last one, what is holding two ammonia molecules together? Intermolecular forces. We're dealing with two of them at the minimum. Okay, so ammonia, you might say, well, before I can answer it, I got to refresh my memory and figure out what is the formula for ammonia. Okay, so that's NH3, polar molecule, hydrogen bonded to nitrogen, hydrogen bridging. Okay, so that's basically how we attack these type of problems. You got to read the question carefully, determine whether you're talking about the atom itself or the interactions with other atoms. Then from there, determine whether it's polar or nonpolar, which then tells you what IMF interaction, if you're dealing with IMF interactions. Okay. All right, this kind of summarizes it. If it's covalent, obviously nonpolar to the left. Anything that's nonpolar gives you London forces. If it's polar, it's going to be either, dipole or hydrogen bridging. If it's hydrogen bridging, then the hydrogen must be bonded to nitrogen, oxygen, or fluoride. Okay, even though it has a dipole, it must be bonded to nitrogen, oxygen, fluoride. And if it's ion dipole, then you're going to have an ion in solution. Okay. All right. Any questions so far? Well, we're going to tie that information into the physical properties of compounds and how they react, okay, to each other relatively. We can't determine the absolute values, but all we can do is compare and contrast and determine who's going to have a higher, what we call vapor pressure. Now, what vapor pressure is, and normally in class I have a soda pop there and I demonstrate it, but I got my big soda pop here. Assuming this is full, we got liquid down here in the container. Well, that liquid, that diet pop, is loaded with carbon dioxide. Some of that carbon dioxide actually eventually goes into the clear area up here. Okay, I got it capped, so I won't lose any carbon dioxide because leave it uncapped, like CO2 goes away and you got a flat drink. Now, if I were to put a pressure gauge here in the air area, I would actually be able to measure a pressure because of the gas molecules that are in the air. Okay, that is what we call vapor pressure. Now think about this for a moment. If the molecules in the water if their intermolecular forces are very strong, they're going to prevent a lot of those water molecules that go into the gas phase. Okay, which means that vapor pressure is going to drop because there'll be less gas molecules. If if the intermolecular forces in the liquid is weak, then there's going to be more of those liquid molecules go into the gas phase, causing the vapor pressure to go up. Okay, so they're all related to the intermolecular forces. As far as boiling point is concerned, again, These are interactions with other molecules. If that interaction is very strong relative to another molecule, it's going to have a higher boiling point. I gave an example of water. Water boils at 100 degrees Celsius. Ethanol boils at 78 degrees Celsius, okay, much less. So the intermolecular forces of water is much greater than ethanol, okay? Surface tension, that's a measure of how much water beads up on the surface, okay? If the forces are very strong, the molecules are held onto each other tightly, they tend to beat up on the surface. A liquid, a drop of that liquid tends to beat up more so than another molecule or liquid that the forces are weaker and their little bead would be probably much less, a lot flatter. Viscosity, that's a measure how thick something is. We all know that water and honey will flow at different rates. If I have a cup of water and a cup of honey and I flip them over, see who's going to win the race, you know from experience, the honey's going to lose. Why? Because it's thicker. That implies that the intermolecular forces of the honey molecules is stronger and the molecules are holding on to each other much greater. Now, how can I get that honey to flow quicker? I heat it up. If I heat up the honey, increase the temperature, guess what? I break up those intermolecular forces a little bit, allowing the molecules to flow much more liquidy, okay? So that's what we're going to be talking about. All right, so I just mentioned vapor pressure, and basically it's just how the molecules are held to each other. If they're held on real tightly, we're going to have less of that liquid going into the vapor phase, okay? Hence, our vapor pressure would decrease, okay? And this is just something you already know. You take the cap off, soda drink, it's going to get flat because the vapor is going to evaporate. So if you have strong IMF interactions, you're going to have lower vapor pressure, okay? Because less molecules will be allowed to get into the vapor phase. Okay? So a good example in the diagram is this one here. In both cases, A has the weaker IMF and the higher vapor pressure, okay? You can see here that A has a lot more gas molecules, which causes that vapor pressure to be greater when we compare it to B, where yes, it has vapor pressure, but it's low because the IMF interaction of the molecules in the liquid phase is much stronger in B than they would be in A. Okay, the boiling point. Strong IMF, we end up with higher boiling point. Same reasoning, okay? We need to break up the IMF interaction so that energy used is used to break the interaction. Surface tension, stronger IMF would give us a higher surface tension. Okay, again, same reasoning here. And then this, here's an example. A here would represent the higher surface tension and would beat up more than B. You can see how it kind of beats up more than B. B kind of flans out. Right. Viscosity, we all know that oil flows slowly, depending on what weight you have, you know, and things like alcohol, very rapidly, low viscosity, okay? So something that has a stronger IMF would have a higher viscosity, okay? Again, because of the interaction of the molecules. So here, we're asked to compare ammonia and fluorine. Okay. Well, first of all, we need to know the formula. So to refresh your memory, ammonia, because we've done that a number of times throughout the chapters, the formulas are NH3 and fluorine and F2. Okay. Well, the next thing we need to find out is, all right, is ammonia polar? And is fluorine, is it polar or non-polar? Well, we know that if we do the Lewis dot structure, ammonia, because the lone pair, is going to be a polar compound automatically. And fluorine is diatomic, so it's going to be nonpolar. Okay, so ammonia would be polar, but the fact that the hydrogens are bonded to nitrogen, its force is the hydrogen bridging force. Fluorine being nonpolar, the only force it's involved with is London forces. Now, then refresh your memory on the previous slides. London forces are the weakest, and hydrogen bridging of the three is the strongest. So that would affect the following questions. So here, which has stronger IMF? Obviously, ammonia, okay, because it has a stronger force. Which has the lower boiling point, okay? Well, the lower boiling point would be the one with the weaker force, which in this case would be London force or from the molecule fluorine. Okay, which one is polar? Well, we defined that earlier. NH3 is polar, ammonia. Okay, fluorine is diatomic, automatically nonpolar compound, which has the higher vapor pressure. Here, the one with the weaker force, which would be fluorine. Then the question is, which is the least viscous? Okay, so fluorine with a weaker force would be the least viscous. And finally, I believe the last one, which has more surface tension, and ammonia will have the more surface tension because of its stronger IMF interaction. Okay. Now, these questions were asked in this mode, but you could easily change that question as number one. Instead of saying which is stronger, you could say which has weaker. Number two, you can say which has a higher boiling. Just invert the question. Okay, so questions can come at you one or two ways. So here, as IMF increases, the viscosity increases. The boiling point increases, and the surface tension increases. Again, as we get stronger IMF forces, the interaction between molecules becomes stronger, so these physical properties will increase, with the exception of vapor pressure. They'll have less vapor pressure. Okay. Now, briefly, we're going to talk about water. It's kind of unique in itself. Water, I mentioned this before, very, very polar, most polar solvent that we have. It has two bonding pairs and it has two lone pairs. Okay, its bond angle much less than 109.5 because of the lone pairs. Okay, it will dissolve many ionic compounds and actually mix with other polar substances. Okay, has very strong hydrogen bridging forces between molecules, very strong, very polar, very high IMF, low vapor pressure. Okay, boils at 100 degrees, melting point 0 degrees, high surface tension. And the unique thing about water, which is kind of rare, that when it freezes, it actually expands. Okay, and its density, it freezes, is much less than liquid water, hence it floats. So ice cubes, as you know, float in water because its density decreases, simply because of the expansion. I went through that scenario a while back. Okay. And it's unique is when it does freeze us, its structure is very ordered. Something interesting about nature. It makes crystals that always picks a hexagonal shape. These are molecules, crystals of water in the frozen state. Very unique material. All right, heating and how it relates to EMF. We have this heating curve here where we're putting energy into the system, we're heating it, okay, along this axis here. And then obviously as we put energy into the system, we're measuring the temperature goes up. So we can make a plot of temperature versus heat. Well, if we start off at a very low temperature, everything's in the solid phase, okay? As we increase the temperature, not the temperature, but the energy, as we heat it up, temperature goes up. So we have a plateau here, okay? Not a plateau, a rise in temperature in the solid phase. Then eventually what happens is we hit a plateau, whereas no matter how much energy we put into the system, that plateau stays there until such time that there's a big jump in temperature again, okay? And guess what? Further down here, we hit another plateau. So we continue to put energy into the system in this second plateau, but the temperature doesn't increase until such time there's a change and then the temperature goes up again. So what is happening in these areas? Okay, this is what's happening. This could be water, for example. A good example would be water. In that initially we got water as ice and we heat it and we increase. Temperature goes up as we add more energy into the system. When it reaches the first plateau, we have a mixture. Now, prior to that, in the rise is basically all solid until we hit the plateau. At that plateau, we have a mixture of solid and liquid. And all the energy that we put in there in that plateau is being used to break up the IMF interactions of that molecule, breaking them up to force those liquids apart further until such time that all that solid has been converted to liquid. And then guess what? We jump the temperature up again, climb up another hill, and it's all in the liquid phase, and we hit a second plateau right here. At that second plateau, we have added a lot more energy. We're here at this stage as far as giving heat to it and energy. Well, at the second plateau, there's a mixture of liquid going to gas, okay? And all that energy that we put into it is simply breaking up the IMF interactions of liquid, forcing the molecules to go into the gas phase until such time that all the liquid has been converted and we have another rapid increase in temperature. So, something to take a note when you're cooking something, and it's boiling, you're not going to get that temperature go any higher or put more energy into it. You're at the plateau, so save your energy. Okay, it won't go up anymore. So that is the heating curve. Be aware of the phase of each one. We got totally solid phase. A first plateau, we got a mixture of solid to liquid. Then we got a total liquid phase as it decreases in temperature till we hit the second phase, where we have a mixture of liquid and gas. Eventually, it goes up to all gas. Okay, and at the plateaus, what we're doing is simply breaking up the IMF interactions of the molecules. Okay, so temperature remains constant. All the interactions breaking up into the IMF interactions. We're not breaking bonds. Remember that. We're not breaking bonds. We're just breaking up the IMF interactions. Okay. All right. And the same is true the other direction. We went heating it, but we can remove heat. And by doing that, we're not breaking IMF interactions, we're creating them as the molecules get closer and closer together as the temperature goes down. That, ladies and gentlemen, brings us to the end of chapter 14. Okay, so if you have any questions, feel free to type it in. If not, I will see you on Tuesday, and we'll finish chapter 15, which is the last chapter. And like I said before, it's a small chapter, so it won't take us too long. And also, it's a good time if you've got questions concerning, problems with respect to the chapters or anything else. So, other than that, if you don't have any questions, I'll see you Thursday. Thank you for showing up. I appreciate it. And stay safe out there.
Hold on 1 second. So you say the next class is next Thursday, not Tuesday, right?
No, Tuesday.
Oh, Tuesday.
Yeah, Tuesday. Tuesday, we're going to finish chapter 15. And then Thursday will be like review time.
Okay. And then the following weeks, we're going to take a test, right? Oh.
You have exam number 3, which opens up on the 25th, and it closes on the 27th. And then the final is May 6th and closes on May 7th.
Okay.
Okay, I got everything on Canvas, so you might go check the calendar there and you'll see all that.
All right.
Okay?
Yes, sir.
All right. Any other questions? Feel free to unmute yourself. There's only 9 of us. All right. Thank you all. You guys take care. What? They delivered it, but was it locked or but they I didn't